Lesson 2, electric field. I would argue this is going to be one of the key concepts of the whole unit. So turn your brain on. Okay? We want to try initially to relate stuff to gravity because we're fairly familiar. We spent some time looking at gravity. The gravitational field, symbol little g. If I ever say gravitational field, that's what I'm talking about. What's the gravitational field here on the Earth, Andrew? 9.8. How do we calculate it? It's two ways. If you're on the Earth, we could drop it and time it and calculate it like an acceleration. But you can also calculate it anywhere in the universe. The gravitational field is big G, big M over R squared. That's not blatantly on your formula sheet. You have to clue in that it's the acceleration in front of the little mass of the gravitational force equation. It reflects the effect that a mass has on the space around it. Here's a planet. Right now, this planet is sending out in all directions a gravitational field. And if suddenly a wandering asteroid comes along and encounters this planet's gravitational field, it's trapped. This planet will exert a force on this planet. This asteroid will also exert a force on the planet, but small asteroid, big mass, the acceleration is going to be fairly negligible here. Big acceleration here. So it says fill in the appropriate relationships. Force of universal gravity, big G, big M, little m over R squared. We had the definition of the gravitational field, which I just gave you at the top of the page. You know what? Let's change colors so it stands out. Big G, big M over R squared. That's how to calculate that. If you crunch that for the mass of the Earth and the surface of the Earth, you'll also get 9.8, which matches our observed data by dropping something. You can also get the gravitational field as a ratio, because we also said on the Earth, gravity is mg, yes? Brett, get this g by itself. How? That's meant to be really easy. You with me? Back here. Get this g by itself. How? Thank you. You can also think of it as the force divided by the mass at that location. That will tell you the gravitational field at that location. So another way of us calculating the gravitational field if we're on a strange planet would be to hang a 1 kilogram mass from a scale and measure the force divided by the 1 kilogram, and that would tell us g on Mars or whatever planet we were on. What were the units for gravitational field? Well, there was two possibilities. But the one that comes out of here is, Brett, what do I measure force in? What do I measure mass in? It was also meters per second squared, as it turned out. But I want to talk about it now in terms of forces, so let's talk about it as newtons per kilogram. Gravitational field. So, example A says, find the gravitational field strength that far from the Earth's center. Calculate the gravitational field strength. What you want to ask is, which approach will I use, the ratio approach or the definition approach? Well, they gave me a distance from the Earth's center. I think I'm going to use the definition approach. The gravitational field strength is going to be that. It's going to be 6.67 times 10 to the negative 11. Mass of the Earth divided by, not the radius of the Earth, but how far we are with the location that we're at, which is, according to this question, 8.38 times 10 to the 6. About 2,000 kilometers up. How strong is gravity about 2,000 kilometers up? Sorry, how strong is the gravitational field? Not 9.8, a little bit less. What do you get? Also good calculator practice, boys and girls. Katie, what? Oh, I thought I heard you. Pardon me? Thank you. Squared! When isn't it squared? When we're doing energy. And then there's an extra m. You get 5.68. Yeah. If you were in a space station at this height and it wasn't in orbit, because in orbit you're in free fall, so you don't have a normal force, you feel weightless, you would feel lighter here. Your normal force would be about 2/3 of what it normally is. Okay. So one way to calculate the gravitational field is if I tell you how big the mass is that's causing the field, the planet, and how far we are from it. Another way to calculate the gravitational field doesn't look at the planet, it looks at the mass that's in the field itself, the small mass. If I have a 10 kilogram test mass and the scale says it has a weight of 750 newtons, what's G? Well, G is equal to the force divided by the mass. I don't think I need a calculator for this. It's going to be 750 divided by 10. The gravitational field strength here is 75 newtons per kilogram. And I wrote meters per second squared here. You know what? I could have also written newtons per kilogram. And since we're talking about gravitational field, why don't I write it that way? I don't know the planet here. I only know the mass that's in the gravitational field. But with that kind of a G, what could you tell me about the planet? Bigger or smaller than the Earth in all likelihood? John, why? Not just bigger, way bigger. What's the Earth's gravitational field? 9. What's this one? Like almost 6 times, well, more than 7 times more. I would have to guess that this is a huge planet, sending out a way stronger gravitational field. And I'm probably not very far away from it, because if I was far away from it, this would be smaller. Even though I don't know anything about the planet, I can make some educated guesses. We're going to define electric field in a similar manner. Okay? That invisible thing between the two charges, a field. We can't see it, but it's like the meter stick that I use to tap Connor upside the head, except it's an invisible meter stick, Connor, and it goes out in all directions three-dimensionally. So now it's a little tough to visualize. We say that an electric field reflects the effect that a charge has on the space around it. As soon as you put a charge into space, it's sending out like an invisible octopus in all directions, tentacles, an electric field in all directions. And if another charge comes along like a wandering asteroid did for the planet, it will get sucked into either orbit or get all the way pulled in like charges attract. Or, but this time now, Brianna, it could go 2 ways, because unlike charges attract, what do like charges do? So unlike the Earth, a charge could come and get repelled as well if they were like charges, which doesn't happen in gravity. Or does it? We're still looking. So it says fill in the appropriate relationships. Force of gravity, we said that was K Q1 Q2 over R squared. Okay. In the gravity equation, what was here and here? Mass. In fact, charge in the electric force equation, Kara, sort of behaves like mass. So, you guys stay on this page. That was gravitational field. Take a guess. What do you think electric field is? Look how we got gravitational field from the gravitational equation. Look at your electrical equation in front of you. Take a guess. Bah! Nothing. Got math. Yeah. Symbol for electric field is capital E. K Q over R squared. Where K is 9 times 10 to the 9th, and Q is the charge that's creating the field. This is the, I'll call it the planetary charge, the big charge that's sending out the field. Not the satellite, not the asteroid, not the spacecraft, not the tiny charge. Oh, definition of electric field. The definition of electric field is going to be how much force on every coulomb of charge that's in that location. How much force on every coulomb, how much force every coulomb of charge experiences. And that gives us the electric field equation as a ratio. The electric field equation as a ratio is the electric force divided by little q. Little q, this is the test charge. This is the satellite charge. In this one, you don't know the planet, but you know what force the charge is experiencing. So you can figure out the electric field at that location. In this one, you don't have a charge in orbit, but you know the planet that's sending out the big charge that's sending out the electrical field. Units of electrical field? Well, what do I measure force in, Brett? What do I measure charge? Sorry? What do I measure charge? Newtons per coulomb. That's the units for electric field. There's a bit of a problem here because if you glance on your formula sheet, they use E for electrical field. They also use EP for potential energy, and it's very easy to get them mixed up. And I told you yesterday, last class, unfortunately, if you find the wrong thing, I have to give you 0 because you found the wrong thing. Also, you'll notice electric field is a vector. It has direction. We're going to talk about that in a second. Turn the page. Let's see if we can help you visualize this a little bit. Okay. I'm going to put a charge, a positive charge, right there. And I'm going to turn on the electric field. The electric field is going in all directions. And you can see it gets weaker and weaker and weaker as you get further and further away. It gets lighter and lighter and lighter. Okay. I can even, we got direction only? Nope. I'll even add the strength like that. I'll put an electric field sensor right there. The electric field gets stronger the closer I get to the planet, to the big charge. Gets further away. Only you'll notice, what direction is the electric field pointing right now? Toward the planet or away from the planet? Away from the charge that's causing the electric field. Unlike gravity, Connor, stuff can fall up when we're talking about electricity. Clear all. What if I put a negative charge? Which way is the electric field pointing now? Towards. Okay. Now let's look at how two positive charges interact. What will like charges do, Brianna? So what this guy is pushing this positive to the right, this guy is pushing this positive to the left. Right here, this guy's pushing in that direction, this guy's pushing in that direction. The net force is kind of up at a bit of an angle. So the electric field tells you the direction of the force as well. The force lines, the direction lines, follow the electric field. really strong and to the left when I'm close to this guy. As I get further away, this charge here is pushing to the right. So as I get further away, in fact, you know what? There's a little equilibrium point right about there where both electric fields cancel each other out because they're pushing in opposite directions. Your net field is 0. What about a positive charge? Okay, what do unlike charges do? They attract. So let's look at the electric field here. It's always pointing to the right because the positive is repelling and the negative is attracting. Back to here. As was the case with electric force, electric fields cannot be negative. A negative answer arising from the above formula simply indicates attraction, so the negative should be dropped in any answer. Josh, you want to help him out? He's not making it very well. Give him an elbow. Or that was a mighty long blink. For this reason, some books will actually put the Q in absolute values. Okay. Example 4, A and B. At a certain point in space, a -5, hey, what was this symbol that we learned yesterday? Microcoulomb test charge. Do me a favor, underline the word test charge. That's our word for, that's the satellite. That's the tiny charge. Experiences a force of 5.2 times 10 to the 4 newtons towards the south. Find the electric field strength at this point. So we have two ways of finding electric field. Electric field is the force divided by the test charge, or the electric field created by the planet. Look at A. Do we know the planet, or have they given us the tiny test charge and the force? We're going to find the electric field here by saying, you know what? It's 5.2. Actually, let's write the equation so that we know what the heck we did. It's going to be the electrical force divided by the test charge. 5.2 times 10 to the -4 divided by 5 times 10 to the -6 microcoulombs. Electric fields are usually pretty big. They're usually in the thousands or in the tens of thousands or sometimes in the hundreds of thousands. How big is the electric field at this location? Don't all rush for your calculators at once or anything. Folks, wake up here. Come on, chop, chop. Yes, you. You tired? You gonna make it? Give me like 5 sighs in the past 3 minutes. What'd you get, Emily? I have no idea what you said. 104? Is that right? Yeah. Oh, it's 0.5. Thank you. So 1,040. Yes, you get a candy, Mitchell. Is it 1,040? Units? Newtons per coulomb. That's how strong the electric field is at that location. B says, find the electric field strength 0.45 meters to the right of a 2.3 microcoulomb charge. Here they've told us the planet, and they've told us how far away we are. That's how I know I'm going to use this definition of electric field, because they gave me a distance, meters. Okay? It's important to know which one to use, otherwise you're going to be going, what do I do? You're just going to sit there and drool. So the electric field here is going to be KQ over R squared. It's going to be 9 times 10 to the 9th, 2.3 times 10 to the -6, divided by 0.45 squared. You get 102,000? Yeah? 102,000 newtons per coulomb, or 1.02 times 10 to the fifth newtons per coulomb. It's this electric field that is acting on charges to move them around. Turn the page. Or next page over. Second key idea. The direction. The direction of the electric field. With gravity, it was never an issue because gravity always attracted. Things fall down, Joel. They don't fall up. But electricity can attract or repel. We need to define a direction. And so here's how we define it. And you're going to underline this in a second. I'm going to highlight it. The direction of the electric field is the direction that a small positive test charge would go if placed at that point. What's the direction? Which way would a positive charge want to move if it could? But it's a small positive charge. How small, Matt? So small that it doesn't have its own electric field, and change the question. So it's an imaginary test charge, we call it. Clear. There's the electric field. Which way would a positive charge right there want to move if it could? Away from this positive charge. That's why that arrow points away from it. Which way would a positive charge right here want to move if it could? Towards the negative charge. That's why the electric field points towards the negative charge. Now I got two charges. Which way would a positive charge right here want to move if it could? Well, it would be attracted by both. It would get pulled to the left and pulled to the right, so it would probably get pulled kind of like that. A little easier to see if we add some motion. Assuming this decides to run. Come on. Okay. File, add a charge. So here's a positive charge. Or is it a negative charge? How can you tell? Look at the arrows. Are the arrows pointing towards or pointing away from this charge? Which way would a positive charge want to move if it could? That's the direction that an electric field is defined as. So if it wants to move towards this, is this negative or positive? Let's add another one. They're going to repel each other. Yes? You can see them slowly interacting. They're somehow magically caught inside this box. It's a simulation. They're going to bounce off the walls of the box. But you can see the electric fields changing because everywhere they go, they change, they add, the two electric fields overlap. Let's add a positive one charge. You can see this one is positive. Pause. That's a negative charge. The electric field wants to move towards there. Positives want to move towards it. What about this one? That's the positive charge right there. There's the negative charge right there. Oh, let's get something really complex. Add a couple more. Now my computer is having to do some serious number crunching. This is some very heavy math here. This is what's going on at the atomic level, for example, in gases all the time. Okay. Example 5. Find the direction of the electric field at a point where the negative 0.5 microcoulomb test charge experiences a force toward the south. This charge right here, is it negative or positive? According to the question, what does it say? This charge right here, with the minus sign on it, with the negative in front of the number? Is it negative or positive according to the question? What does the question say? Please, for the love of God, help me here, people. Negative. Which way does the negative feel a force according to this question? South. Which way would a positive want to move then? Think about it. Emily. The electric field is north. If a negative wants to move south, a positive wants to move north, and electric field direction is defined as which way would a positive want to move if it could. There's a shorter version of that, Sean. Electric field is defined as from positive to negative, because electric fields would want to move from positive to negative, from positive to negative. Find the electric field direction right there. Okay. Which way? Oh, this charge, is it positive or negative? Is there a minus sign in front of that number? This charge, is it positive or negative? Which way would a positive test charge right there want to move if it could? Emily, please, thank you for being with me now. Sigh girl. Yes, what? And yes, Andrew, I heard you too. Thank you. To the right. What direction is the electric field right here? Down. What direction is the electric field right here? Up and left. If we had more information, we'd actually do some vectors and trig. How do we draw this? We represent electric field with lines. So it says, draw the electric field around a positive charge. We represent the electric field, or any fields, with lines with arrows on them. First of all, the electric field right here, what direction is it? Up, down, left, or right? Which way would a positive want to move right there if it could? Up. What about here? What about here? Okay, here's how we draw electric field. With arrows. Now, this is an approximation because, Nicole, in real life, there's trillions of lines. Well, in fact, there's an infinite number of lines flowing out from the charge because they're going out in all directions, and they're also going out in 3 dimensions. So here's what we have to come up with. This is our convention. We'll represent the electric field with lines. If this charge was twice as strong, add this, please. Twice as many lines means twice as big a charge. What if I wanted to show that the charge was 3 times as big, 3 times as many lines? Okay. So that doesn't mean that this charge is 1, 2, 3, 4, 5, 6, 7, 8 coulombs. All it means is it's twice as big as some other charge on the page if the other charge had 4 lines. Second thing is, the closer the lines are together, the stronger the field. Here, don't write this down. I'm going to gum up this diagram. The distance between the lines is about 1 centimeter on my piece of paper. Here, the distance between the lines is about 2 centimeters. Here, the electric field is half as strong as here, give or take. Further the lines are apart, the weaker the field at that point. That's our convention. So, draw the electric field around a negative charge. Okay. Which way would a positive charge right here want to move if it could? How big is that negative charge compared to this positive charge? Half as big. But I don't know anything more than that, but half as big. The real fun begins when you got 2 charges and they start to interact. So, direction of the electric field. From positive to negative. Or we ask, Which way would a positive test charge want to move that could? I find that second one more useful because sometimes I don't have a negative or a positive charge in my diagram. I only got one of them. And so when I think from positive to negative, I'm missing one. But I can always think, okay, which way would a positive test charge want to move that could? Because like charges repel and unlike charges attract. I'm going to pause here.